VSWR ANTC Department, PICT Pune. Today we are going to perform the new practical of RMT subject, that is measurement of VSWR. Measurement of VSWR. So our title is to measure and verify voltage standing wave ratio with respect to open, short and match termination by using the slotted line section. So for a VSWR measurement purpose, we will use this is our block diagram. This block diagram. In a block diagram, already we used mini blocks in a previous experiment. Our first block is nothing but a klystron power supply. We know the use of this power supply. Second block is a klystron tube. It is also known as a reflex klystron tube. Here, this tube acts as an oscillator. It generates a electromagnetic signal at a X band, that is from 8 giga to 12 giga. And we know from 8 to 12 is nothing but our microwave frequency. Third block is a isolator. We know the operation of isolator here. Isolator avoid the reflected signal from the output side, and it keep the stability of operating frequency of a oscillator. Our next block is a cavity resonator. We know the function of cavity resonator. It is used to measure the operating frequency of our reflex klystron. That's why this cavity resonator is also known as a frequency meter, microwave frequency meter. Our today's experiment is nothing but a study of VSWR or measurement of VSWR by using the slotted line section. Yeah. So here we will use a slotted line section in this block, and we will use the different type of termination like a match termination, open termination and short termination across the slotted line section. So look here, this is our slotted line section. The question comes in a mind, why it is known as a slotted line section. So you look carefully this waveguide. Here this terminal, this two terminal end is nothing but my waveguide. Right hand side is a port 1 and left hand side is a port 2. And look here, the slot is present inside the waveguide. That's why it is known as a slotted line section. Yeah, slotted line section. In this slotted line section, here this is our probe. This probe we can vary by using this knob. We can change the position of the probe, and inside the probe means here we are using a detector, and we know our detector is a Schottky barrier detector. Okay. Now this probe is a tunable probe, means we can change a input or impedance of this probe. So this portion is used to determine or to match the impedance. You look here, it is varying. Yeah. Now question comes in mind, how to determine VSWR by using the slotted line section. Before doing an experiment, you should know what is the theory related to the VSWR. So I will explain the theory of VSWR first, and then we will see how to measure the VSWR by using the slotted line section. Yeah. So look here, this is your waveguide. Yeah. If you check a front view of this waveguide, it looks like a two line. So I will draw here. This is your first line and this is your second line. Yeah. Now apply the some AC voltage to this waveguide. So this is your AC input, and connect some load across a waveguide. So let us assume this is your load. Yeah. So according to the maximum power transfer theorem, when the input voltage we apply across these two terminals, so impedance across these two is nothing but your Zin. Input across this terminal is nothing but a Zin. So according to the maximum power transfer theorem, when your Zin perfectly match with a ZL, that time maximum power is delivered to the load. But if your load impedance is not perfectly matched with a input impedance, that time some wave reflected back towards a generator. Yeah. So in a waveguide we have two type of wave. One is forward wave and another is a reflected wave. So when two waves are present inside the waveguide, these two waves creates a new wave, and that wave is known as a standing wave. That standing wave not propagate in a forward direction or backward direction. It just goes up and down, up and down. And if we measure some voltage across this waveguide, means if we take some graph, this is a distance of your waveguide and this is a magnitude of your waveguide, means a voltage. Yeah. So if we draw the voltage standing wave on this waveguide, it looks like this. Due to the mismatch. So in which this voltage is known as a Vmax voltage and this voltage is known as a Vmin voltage. Yeah. So according to this theory, we can define the voltage standing wave ratio. So here voltage standing wave ratio VSWR is defined as it is the ratio of maximum voltage to the minimum voltage. It is the ratio of maximum voltage to the minimum voltage. But here we can't measure the Vmax and Vmin directly. Yeah. Theoretically, let us see what would be the ideal value of VSWR, and then we will perform the actual performance character or actual parameters of VSWR. Practically, we will measure the VSWR parameter, means Vmax voltage and Vmin voltage across the slotted line section, or by using a slotted line section. But theoretically, first of all, see what would be the value of your VSWR. Theoretically, we can write this VSWR in this way: 1 plus mod of tau divided by 1 minus mod of reflection coefficient. So this parameter is known as a tau, or the meaning of this parameter is nothing but a reflection coefficient. Yeah. And we know how to calculate the reflection coefficient. Already we have seen in a previous year or in a electromagnetic subject. Yeah. We know the reflection coefficient across any transmission line or across any waveguide, we can calculate by using the ZL minus ZO divided by ZL plus ZO. Yeah. Here ZL is nothing but this impedance, and ZO is nothing but characteristics impedance of waveguide or transmission line. Yeah. So when you are Zin, this Zin and Zr both are matched to each other obviously. But if your ZO or Zin are not matched with a ZL, that time you will get a reflection coefficient. So look here, what will be the case for reflection coefficient and how to calculate a VSWR. When your ZL is equals to matched means when your ZL is perfectly matched with a ZO or we can say Zin, that time this portion becomes a 0. Yes, ZL minus Z0 becomes 0, and this may be some value like a ZL plus Z0. So 0 divided by something is nothing but 0, and hence our ideal case, this is a termination and this is a VSWR. Yeah. My termination is a match, so I will write here. This is a match. So in match termination, what would be my VSWR? If I put the reflection coefficient is equal to 0 in this formula, we will get a VSWR is equal to 1. So ideally the voltage standing wave ratio for a match condition is equal to 1. Let us see what would be your VSWR for a short and open case. So first of all, take a open. Keep your impedance is equal to open. Means load is equal to open. There is no any load available across a waveguide. This case. So according to the electromagnetic theory, we know when your transmission line is equal to the open, that time your load is act as a very high, and very high means a infinity. If I put the value of infinity here, means very high, so we know this part is neglected. So some high divided by high, so my reflection coefficient is nothing but 1. If we put a 1 in this case, so look here, 1 minus 1 is 0. Something divided by 0 is nothing but a infinity. Yeah. So VSWR across a open case is nothing but a infinity. So here for a open termination, means for a open termination, ideal case for a VSWR is nothing but a infinity. Yeah. Now my third case or last case is nothing but my node is a short circuit. Short circuit means my ZL is equal to 0. If I put my ZL equals to 0 here and here, so what will happen? My answer ZO divided by ZO, but this is a minus. So my magnitude of reflection coefficient is 1, but some minus angle. But we know this reflection coefficient is a phasor quantity. Here we can write the magnitude is 1 and angle is 180 degree. Yeah. And in open case we can write 1 magnitude and 0 degree. But here we are using only magnitude. So put the value of reflection coefficient as a 1 here. So again see, 1 minus 1 is a 0 and something divided by 0 is nothing but infinity. So in a short termination, your ideal case of VSWR is also the infinity. Yeah. Now question comes in mind, how to measure the VSWR in our lab by using a slotted line section. Now look here. I told you this is my slotted line section. We will use this slotted line section here. So look here. This is the position of your slotted line section. Now apply some input to this port. Keep this probe position towards the load, because we know we are measuring the VSWR and reflection coefficient from the load side, and here use a match termination. So use a match termination means, look here, this portion is known as a match terminator. So impedance of this port and impedance of this port would be the same. So our case is like this. This is a match termination. Now question comes in mind, how to measure the magnitude. Which magnitude? Vmax and Vmin magnitude. So what we will do, we will connect this probe to the CRO. This is the detector, means this portion, and here we will connect to the CRO or DSO. Yeah. Now our step is to vary your slotted line section from load side towards the input side. So obviously we will get this type of waveform. Obviously, sometimes you will get a Vmax, sometimes you will get a Vmix, sometimes you will get a Vmax, sometimes you will get a Vmin. Yes. And then we will measure the Vmax voltage and Vmin voltage with respect to your waveguide. Yes. So this is the first case. Your termination was match termination. Now second case, your termination is open. In open, keep your slotted line section like this. Here connect your oscillator by using these blocks. Okay, and keep this terminal means load terminal as it is open, and connect your probe of CRO to this detector, and again do the same thing. Vary your probe position by using this knob from right side to the left side, or we can say from load side to the input side in this way. Yeah. Again similarly you will get this type of waveform. Vmax, Vmin. It is not necessary that you will get always Vmax first. You will get a Vmin also. It is depending upon your termination. Yes. And last termination is nothing but a short termination. In short termination, what we will do? We will keep your slotted line section position like this, but we will use this portion as a slotted line. In electromagnetic, we know any conductor act as a short circuit. Yeah, any conducting circuit. So what we will do? We will connect this terminal, this slotted line section to this sheet like this. We will fix. This condition is known as a short circuit. Yeah. So look here. Keep your short circuit like this and vary your probe from load side towards input side like this. Again we will get a same type of waveform. Vmax, Vmin, Vmax, Vmin. Yeah. And then we will calculate Vmax and Vmin. Any value. you measure your value of Vmax here or here, anywhere you will get a constant. Yeah. If you measure the Vmin here or here, you will get a constant. Yeah. And we know the distance between two maxima is a lambda by 2. And distance between one maxima and one minima is a lambda by 4. Yeah. So in this way, we will measure the VSWR with respect to the different termination like a match, open and short. And we will check our reading of VSWR with a ideal condition. Okay, thank you.
Hello students, welcome to Radiation and Microwave Technique Laboratory. Today's experiment is related to measurement of VSWR, that is voltage standing wave ratio, and that VSWR can be calculated for three different conditions: open circuit, short circuit and match termination. To measure VSWR in three different conditions, here you can use the slotted line waveguide section to measure VSWR. Why the slotted line section has been used to measure VSWR, that is already explained in the theory. But in a brief, in short, you can say using the slotted line section, I can move the probe so that wherever maxima and minima can be observed because of different reflection from the load side towards the source side can be observed. Let us see how this VSWR can be measured for three different conditions. Now let us use the same microwave bench which is operating at X band frequency, which is in the range of 8 GHz to 12 GHz. So again, the similar setup of X band source can be used to give the signal to the slotted line section as an input, and using the slotted line Vmax and Vmin, we can able to calculate the VSWR. Once again, give a look over here to the power supply which is driving the reflex klystron, whose beam voltage that has been set is 2.246 volt DC. Beam current for that beam voltage is 14 milliampere. It should not go beyond 20 milliampere. Repeller voltage 246 volt DC. So again, in this setup, essential components are source, which is nothing but reflex klystron with cooling provision. Isolator is essential component. Variable attenuator, optional component. If you want to reduce the magnitude of the source, that can be able to reduce. Then frequency meter, which is having principle of cavity resonator. So if you want to measure frequency inside the waveguide, you can be measured using this cavity resonator. So complete setup output is given to the slotted line section, and under the slotted line section, tunable probe has inserted. So you can see this probe which we can tune by changing its impedance. We can move it up and down slightly, and wherever we are getting the maximum output on the oscilloscope in the square waveform, there we can stop tuning it. So this is the pickup point, and internally it has a diode, and then diode again it is going to the oscilloscope. So basically the modulated signal which has been launched inside the waveguide, that can be detected, and the modulating signal will be back as a square wave. So it is inserted inside the slotted line section, and we can rotate it towards the end or the termination side of the slotted line section. Now the situation, if you will observe, I have not connected anything to the other port of slotted line section. So I can say this is the open condition, open impedance that can be coming at the end of the slotted line section. For short circuit observation, we can connect it with the shorting plate at the end termination. For matching, a match termination can be used, which we can connect over here as a load. So as per the open, short and match termination, we can be able to measure two voltages. One is V max and V mean. Now let us move towards the measurement from the extreme load side towards the source side by moving this knob slightly and keep observing oscilloscope. Let us measure the condition for open termination. The tunable probe is connected to the slotted line section, and the output square wave you can observe on the oscilloscope with its magnitude. Now keeping this as an open termination, now I can move towards the source by using this variable movable knob to measure the maxima. So I am moving towards source. So at one particular point I can get maximum square wave output. So the magnitude is 126 millivolt as a maxima. So at the V max position means while turning the slotted line section, wherever we find maximum square wave magnitude, that voltage we can note down as V max voltage for the open termination condition. So it is 164 millivolt. Now let us measure V mean position. So keep turning using this knob. We can see it is reducing the magnitude of the square wave, output square wave, and which is almost 44 millivolts. Now let us note it, V mean as 44 millivolt. So I can immediately able to calculate V max upon V mean, which is 164 millivolt divided by 44 millivolt. So it comes 3.72 as a VSWR. Now let us measure V max and V mean by shorting the load termination. So I am shorting it with the short plate. So the V max and V mean I can able to measure. So I am keeping the load termination as short. So again from load to source we should move the tunable probe and can able to measure V max and V mean with the similar procedure. So I am moving it for measurement of V max. So it is showing 1 So the maximum magnitude is 168 millivolt. Let us note this 168 millivolt as Vmax, and now again move towards the source so that we will get minimum. So I am moving towards the source. It is still reducing, still going down, down. and it is reaching almost to 0. Here it is showing 6 millivolt as minima. So once again we will note it, 6 millivolt as minima. So student, if you keep on turning it, you can observe it will repeat the same thing. Vmax will be there, again minima will appear, again Vmax and Vmin. It shows inside the waveguide you can have the standing wave signal into it. So it will have Vmax, Vmin, Vmax, Vmin, Vmax, Vmin. Now to go for third observation, which is for match termination and getting its VSWR, I have now attached match termination to the slotted line section as a load. So load impedance is now as a match almost to the slotted line section. Now once again we can repeat the same procedure to get the Vmax and Vmin. So I am moving it again towards the source side so that I can able to get maximum square wave signal. So this maximum square wave signal is 162 millivolt. Let us note it, 162 millivolt as the maximum. And let us move towards minima, getting the minima. So I am again going towards the source side. So here students, you can understand, here it is minima. So let us note minima. It is 106 millivolt. Let us note 106 millivolt. So we can able to calculate now VSWR. So Vmax is 168 divided by 6. So it is 28, which is going to very high value. For match, 162 divided by 106, which is coming to 1.52. So this observation is the practical observation in the case of open termination, short termination and the match termination, which we have observed practically. Now let us understand theoretically, which already Professor Hake has explained you on the board. Let us revise the few things for getting or comparing theoretical value with the practical values. It has been already informed or instructed you to calculate VSWR practically. We can use this equation, Vmax upon Vmin. VSWR has another relation with reflection coefficient tau. So VSWR relation with tau is 1 plus mod tau and 1 minus mod tau. For calculating VSWR, we always use the magnitude of reflection coefficient. It can be the reflection coefficient. It can be imaginary and real value. So only magnitude, real value that we are considering to calculate VSWR. Reflection coefficient relation with impedances is ZL minus ZO, which is characteristics impedance of the waveguide, and ZL divided by ZL plus ZO. So using these three equations, we can able to compare it with the theoretical and practical observation. Let us move for match, open and again third short condition. So if it is a match termination, ZL is equal to ZO. If it is totally matched, characteristic impedance of a transmission line, if it is completely matched, ideally match with the load what you are connecting, then ZL, it is a match condition which we call ZL equal to ZO. So let us put this ZL and ZO value into the reflection coefficient tau. So ZL minus ZO upon ZL plus ZO, if it is same, it becomes 0. So if reflection coefficient is 0, VSWR, which we have seen, is 1 plus reflection coefficient upon 1 minus reflection coefficient. It becomes 1 plus this 0, reflection coefficient 0 here, and 1 minus 0. So VSWR in a matching condition, or we can say in an ideal condition, we will get as 1. So VSWR equal to 1. In case of open termination, ZL, the load impedance, it can be high because the termination is not there and it is almost the intrinsic impedance, open space impedance offered to the termination of waveguide, right? So let us move again for the similar calculation. Here ZL is high. It is not similar to the characteristic impedance of a transmission line, which we can say approximately 50 ohm impedance. So this is high value and this is low value. So which is very negligible as compared to the ZL. So we can say it is almost ZL. So reflection coefficient becomes ZL upon ZL, which comes almost 1. If we put this reflection coefficient 1 into the VSWR equation, we will get 1 plus 1 upon 1 minus 1. So it is infinity. So if it is mismatch and like open termination, it is moving towards infinity. For short circuit condition, the load what we connect is a shorting plate. So load impedance we can say 0. If we put into the reflection coefficient, ZL is 0, 0 minus ZO, 0 plus ZO. Reflection coefficient comes as minus 1. This minus 1 we can write as in a magnitude and angle as 1 angle 180 degree. So if we again put it into the VSWR equation, we can able to calculate VSWR, which again comes as infinity, or you can say very high value. So if we compare theoretical or ideal conditions with the practical condition, you can understand, you can compare. Open, here you got more than 1 or more than 2. Short circuit, you can understand it is moving towards 28 and maybe beyond that it can go. And for match, it is going towards close to 1. In practical or in an industrial application, many times maximum value of VSWR that can be considered is 2. Below 2, 1 to 2 can be acceptable. If the VSWR is going beyond 2 value, it means there is a mismatch and there can be the reflection towards the source, and that cannot be accepted. Similarly, as I have connected the match load and the other open condition and short circuit condition, one can connect directly horn, waveguide horn antenna over here. If I connect that as a load, that horn antenna impedance I can able to calculate by measuring VSWR with the similar procedure. So again connect horn antenna as a load, move this to get Vmax and Vmin. Once you get Vmax upon Vmin, you will able to calculate reflection coefficient. If you find reflection coefficient, ZO is known, which is characteristics impedance. So you can be able to calculate the unknown impedance ZL. This is how in this experiment one can measure unknown impedance using this slotted line section. So the application, if you try to understand, slotted line section will give the better idea to measure or to verify VSWR of known or unknown impedances or open circuit or short circuit impedances. So with all this setup, you can draw a conclusion whichever things that I have been explained to you about VSWR. Thank you.